In this section, we're going to learn how to find the domain of a composite function. And these types of domains are very dependent on the domain of each of the component functions. So let's go ahead and see why this is true. Here we have the domain of our function f, the domain of our function g, and the range of our function g. Underneath our map f, the domain of f is mapped to the range. So this black blob in the middle is the range of f, and this is how it intersects the domain of g. So part of the range of f is contained in the domain g. And then underneath the map g, the range of f is mapped inside the range of g. Here we have the range of g of f. So if this is the range of g of f, then the range of f is given by this piece here. And then finally, if we pull this back one more time, here is our subset contained inside the domain of f. In this example, we see that the domain of g of f is elements in the domain of g that are also in the range of f. And the domain of g of f in this case is this colored in piece here. Now let's look at a definition. The domain of a composite function is all x values in the domain of f for which f of x is in the domain In example 5, we're going to go and look at how to find the domain of a composite function using an example. Where we're given that f of x is equal to 1 divided by x minus 2, and g of x is equal to the square root of x plus 4. There's 3 steps to determine the domain of this composite function. First, we need to find the domain of g and the domain of f. And then, afterwards, we need to find all the output values of g that are contained inside the domain of f. So the domain of f can be found by looking at our function. And we know that this function is going to be defined everywhere except for where the denominator is equal to 0. The only time the denominator is equal to 0 occurs if and only if x minus 2 is equal to 0. This means that x is equal to 2 is not part of the domain. So the domain of this function is going to be negative infinity to 2, open parentheses, union 2 to positive infinity. Let's look at the domain of g of x. G of x is the square root, and g of x is the following function. We know that the square root function is only defined when the argument is greater than or equal to 0. So the restriction that we have on this here is that x plus 4 is greater than or equal to 0. X then is greater than or equal to negative 4. Writing out the domain of g of x using interval notation, this is going to become a negative 4 to positive infinity, where we include the negative 4 inside our interval. On this new page, let's go ahead and just draw out what the domain of our function g and the range of our function g is going to be. So this red number line represents the domain, or the possible numbers that can be in our domain. And we just found that all real numbers greater than or equal to -4 is in our domain. So all these numbers over here are part of the domain of our function. Underneath our function g, this is taking a set of y values. And we know that if we place a number inside the square root, this number is always going to be a positive number. So the range of this function is going to be given by all numbers that are 0 or higher. So if this is 0, then the range of g are these numbers over here. Now the domain of f is going to be all numbers except for the number 2. So here is our domain of f. And now all we have to do is find the intersection between the domain of our function f, which is given by this number line here, and where it intersects with the range of our function g here. So g is going to be all real numbers from 0 to infinity, and the domain of f is going to be all numbers except for the number 2. So let me go ahead and superimpose the range of g onto the domain of f. And I'm only going to color in their intersection. So this is going to go from 0 to 2, but it's not going to include 2. And it's going to go from 2 to infinity again, not including 2. So this represents the domain of f composed of g.